Hi, this is an example problem from Chapter 14 on the ideal gas law. Pause for a moment and read the question. So in the ideal gas law, basically we're looking at some properties of a gas and seeing what happens if you change some of the properties. How does it affect the other properties? Let's look real quick here. So we've got N, little n, the moles of a substance, P, the absolute pressure of the gas, the volume of the container the gas is in, T, the absolute temperature. Those are the important variables for the ideal gas law. And the ideal gas law itself relates those variables. There's two ways to write it. Whether you want to use little n moles, then you use the capital R constant, universal gas constant. Or if you want to use capital N, the number of particles in the gas, then you use K or KB, Boltzmann's constant. So either one's good. And there's the ideal gas law. Let's go ahead and write that down. PV equals nRT. Typically in the ideal gas law, we'll look at a gas that undergoes a change so that the state variables, these variables in the gas law, will change from one state to another. And so usually go ahead and write down initial for the starting conditions, and final, after some change, what are the new values, right? And so we've got four variables here because R is just a constant. We've got the initial pressure, the initial volume, we've got the initial, let me do temperature next, initial temperature, and the initial number of moles of gas, right? And we've got the same thing here for the final situation. And we want to go ahead and try to figure out what these are. All right. So let's see here. The air in the bottle is initially at atmospheric pressure. So that's our absolute pressure. It's just atmospheric pressure. 1.01 times 10 to the 5th pascals. The temperature is 30 degrees Celsius. Remember, we need to be in absolute pressure and absolute temperature. The pressure already was absolute, but the temperature is not. We need to add 273. So 30 plus 273, 303 Kelvin. Always use Kelvin with the ideal gas law. The beachcomber heats the bottle over a fire, and the cork is ejected when the bottle reaches 99 degrees Celsius. So again, we need to add 273 to that, and that's going to give us 372 is the final temperature in Kelvin. What else do we know here? Something about the cork has a mass, it has a cross-sectional area. That's not going to matter for the gas itself. We're also interested in knowing if any of the variables in the gas law don't change. And it turns out that you can assume the volume of the bottle remains unchanged. So these are the same. V final is equal to V initial. These two guys are the same. And since the bottle is closed, before it pops that cork, right? These guys are going to be the same as well. And so that's going to help us a lot here, knowing those are the same. So the way I like to solve these problems, let's see how we do this here. So part A. I want to figure out what, in part A, the pressure was. What is P final right before it pops the cork? So we're going to try to figure this guy out right here. I'm going to do it like this. P final, V final equals N final times R times T final. Now notice that these two sides are always equal in the ideal gas law, right? And what I'm going to do is do a little trick here where I'm going to divide both sides of the equation by something that's equal. The thing that's equal I'm going to use is the ideal gas law and the initial condition. So P initial, oops, we're using this, times V initial, right? We know that that's equal to N initial R T initial because they're the two sides of the ideal gas law. But now look what we can do. The things that are the same, they divide out because they haven't changed. So V final, V initial the same, they cancel. The number of moles at the end and the beginning, the same. And R is just a constant. Those cancel out as well. So this simplifies our equation quite a bit, right? Afterwards, this is all we have left here. We've got P final over P initial is equal to T final over T initial. And if we want to solve for P final, all we need to do is multiply both sides by P initial and plug in our numbers. So P initial, 1.01 times 10 to the 5th pascals, multiplied by the ratio of the two temperatures, same unit, so you can forget about the Kelvin, they'll cancel. And when we plug that in, we get a number, 1.24 times 10 to the 5th pascals. So by heating the bottle at constant volume, constant number of moles, we've increased the pressure there. The atoms are more active at higher temperature. They push harder everywhere. The pressure is greater. Let's look at part B real quick. Part B says, as the cork pops, calculate the force exerted on the cork due to the internal pressure inside the bottle. Well, this is just going back to chapter 11 with pressure. We know that pressure is equal to the force divided by the area, and the pressure in this case is due to the gas inside the bottle. The area that it's pushing on is the bottom section of the cork, and the force that that pressure generates, that'll be equal to the pressure right before it pops times the area. That's the pressure we just calculated in part A. Let's write this as newtons per meter squared, so the meter squared will cancel because the area here is 2.3. Well, we got centimeters squared, right? We're going to have to do a little conversion here. 100 centimeters per 1 meter. We got to square both of those. That means we'll square this, and we'll square that, and we'll square that, right? And when we do that, we're going to cancel out our centimeters. We're going to cancel out our meters squared, and we're going to be left with newtons. And plugging all that into the calculator, remember to square your 100 in the bottom there. Comes out to 28.5 newtons of force that the gas in the bottle exerts on the bottle cap, or the cork, which is enough to, I guess, cause it to pop out.